Hello and welcome. In today's presentation, we are going to be discussing nickel-free steel alternatives for dyed aluminum. Hi, my name is Jacqueline Cook and I work at the lab for Reliant Aluminum Products. Reliant and Clariant work hand in hand to supply the anodizing industry with the experienced, dependable, customer-driven service of Reliant with the highly regulated and top-notch products from Clariant. So why are nickel seals used in the first place? Well, generally for color anodizers, they have been used since the 40s and they've kind of been the go-to for a variety of factors. Dye bleeding, which can affect the color of the final product as well as the age of the bath, improved lightfastness, and overall seal quality are the most prominent factors. While the outcome of these can change based on many other variables, nickel seals have generally guaranteed an overall better result. So the future of nickel seals. Why do we want to find a nickel-free seal alternative? Well, new environmental and medical studies are bringing to light the fact that nickel salts could be suspected carcinogens, which can cause cancer and skin dermatitis. According to California Regulation Prop 65, it is already considered a carcinogen. Globally, the EU, China, and many large OEMs are working to eliminate the use of nickel seals completely. In this presentation, we are going to be looking at different seal chemistries, their types and uses, bleeding and factors that can affect it, a focused dye discussion, and the results of tests run in the lab. All right, so let's take a brief look at the different seal chemistries. These are generally broken up into three separate categories. We have hot seals, which have to run at over 200 degrees Fahrenheit. This means that they have to basically be close to boiling. And this is a deionized water and nickel acetate, both with a smut suppressant. Hot water seals, or hot seals in general, work by hydrating the surface of the pore and using heat to close the pore. This will cause smutting, which is why we have that smut suppressant added. Next are mid-temperature seals. That was my cat, sorry. These run from 170 degrees to 190 degrees Fahrenheit. And include a nickel acetate seal and a nickel-free seal, both with surfactants. This surfactant is added to increase seal quality, but will usually also increase dye bleeding. Many people, not many people, but some regulations don't want to have a surfactant in the seal, so that's another issue to consider as well. But these also work on as similarly to the hot seal by hydrating the surface, but without that high heat, it has to work a little bit differently. Finally, we have a low temperature seal, which runs around 75 degrees or room temperature to about 95 degrees. And this includes a nickel fluoride seal. There are many pros and cons to these different seals, but we're going to go over them a little bit later in the presentation. First, let's go ahead and look at seal popularity. So seal popularity for colored anodizers in the American market, and based on our estimated sales, the most popular seal used is that mid-temperature nickel seal. This is used about 50% of the time, followed by a hot nickel and low temperature nickel seal. So nickel seals are generally the most popular for colored anodizing because the nickel on a molecular level helps the dye structure adhere to the inside of the pore. At the very bottom, you can see used about 5% of the time each is hot water and that mid-temperature nickel-free seal. And they're only used about a fraction as much. All right, so let's go ahead and talk about the purpose of our tests. We wanted to examine the various methods of sealing black anodized aluminum for their effects on dye bleed, seal quality, and lightfastness. These are those main factors that we look at when we are seeing if we have a good seal. And then for seal quality, or not for seal quality, for dye bleeding, that also contributes to the life of the bath and the look of the final product and quality of the final product. All right, so dye bleeding, a few notes. It is definitely dye dependent. Not all dyes are the same when it comes to bleeding. Some will just bleed more than others. Dye activity also has a high impact on dye bleed. This means that when you have an older aged bath whose activity is lower, it will bleed more. Age and use of the bath. So as that bath does get contaminated, it will bleed more. Activity will have a positive effect on dye bleeding, meaning it will bleed less. This activity enhancer or buffer. And temperature also has an effect on it. So a higher temperature means that there will generally be less bleeding in the bath. That heat will force the molecular structure of the dye to adhere better to the inside of the pore. So going into the seal, it will bleed less. It is also highly seal dependent. Nickel seals will generally see less bleeding because the nickel helps to chemically bind the dye bind the dye to the inside of the pore, as I said before. The effects of a surfactant. A surfactant actually has a negative effect on dye bleeding. So while it does increase overall seal quality, it will also increase bleeding in the seal. Seal activity. So depending on the seal, they can last a few months to a year, and some people push it even farther than that. But as a seal does age, it becomes less active. This means that in order to get a good seal on your part in an older bath, you will have to seal for a longer amount of time. And the longer a dyed panel is in a seal, the more time it has to leach dye out into it. So yes, age and use of the bath. And then temperature as well has a pretty big effect when it comes to dye bleeding. The higher the temperature usually means that it will seal faster and it'll give it less time to bleed. So for our focus dye, we are going to be working with a black chromium metallized azo dye. We chose this because everybody runs black, and this specific dye is chosen by 40% of US color anodizers. We actually took a sample from a job shop, so it's an old used dye bath, and analyzed it, and it's at about 75% activity. This means that compared to a 10 gram per liter standard, this bath, even though it reads nominally at 10 grams per liter, is functioning closer to 6 to 8 grams per liter. This also means that it is a bleeder, so we can hopefully better see the effects of the bleeding into our seals. All right, so let's look at our process conditions for the 3 tests that we're going to run first. So for each test, we used a 5005 sheet of aluminum, anodized all of the panels for each set of tests together to ensure consistency, and anodized them in a 180 gram per liter sulfuric acid bath that had 11 grams per liter aluminum in it. We anodized at 70 degrees Fahrenheit at 15 amps per square foot for 35 minutes. This gave us a 0.7 mil coating. For the dye, we dyed at 140 degrees for 15 minutes in a 10 gram per liter bath. All of this is within range for type 2 anodizing, and for the dye, it's within range on the TDS for this specific dye. And then seal is how it's going to differ. So we're going to go ahead and look at the next slide and start our first test. So for our first test, we compared 5 different seals. We compared the hot nickel, the mid-temperature nickel, the hot water, and then a diluted mid-temperature nickel-free seal at 2 grams per liter, and a mid-temperature nickel-free seal at 20 grams per liter. You might hear me say mid-temperature 2 and mid-temperature 20, something like that, in order to abbreviate this a little bit faster. You'll see on the right here, we have pH, temperature, and the time, 20 minutes for all of them. pH and temperature are run within the recommended limits. And so is the concentration for everything, including that hot water. It does have a 2 gram per liter smut suppressant in there, which is recommended on that product's TDS. All right, so let's go ahead and get into it and look at the results. So first for dye bleed, we looked at chromium concentration. As you remember, we used a metallized chromium azo dye. So that chromium concentration at parts per billion kind of gave us an idea of quantifying seal bleed versus looking at it visually. As you can see here, the high temperature nickel and mid temperature nickel did the best. Meanwhile, the mid temperature nickel free seal at 20 grams per liter did by far the worst. Results were greatly increased for that 2 gram per liter nickel free seal. So for seal quality, we performed ADTs, which I'm sure many of you know about, but it basically has us submerging the sealed panels in a diluted acid solution at a controlled temperature and time. The passing grade for this test would be 2.6 grams per liter. So all of these did pass, but a lower number is always better. These are fresh baths, so we want to see the lowest numbers possible. So as a bath age, these numbers will go up, and starting at a lower number is obviously better. As you can see here, the high temperature nickel seal did by far the best. And so while we saw decreased bleeding in that 2 gram per liter nickel free sample, it was at the cost of a good seal quality. So for test 1, let's kind of go over those results. For a 20-minute single stage seal, a high temperature nickel or mid temperature nickel surfactant seal did outperform the others. Boiling water performed well, but mid temperature nickel free seals did bleed when used at a normal concentration. Again, that low concentration of bleeding was curtailed, but it was at the expense of the seal quality. So let's go and look at our second test. For our second test, we decided to try a 2-step process. The first step being a 2 gram per liter nickel-free seal, followed by that normal concentration of a 20 gram per liter nickel-free seal. As you can see to the right, for pH and temperature, these are in the recommended ranges at 185 degrees, 5.5 for both baths for the pH. In that second chart below, on the far left and far right columns, you can see 0, 30, and 30, 0. This means that for that first one, the whole 30 minutes is spent in the 20 gram per liter bath. And for that last one, the whole 30 minutes is spent in the 2 gram per liter bath. This is to not only give us a comparison for what's in the middle there, but also to compare what that additional 10 minutes will give us in comparison to the samples we ran in test 1. So you can see that breakup 0, 30, 228, 426, 624, 1020, etc. And let's kind of see what these results give us. So for seal bleed, we ended up testing it relative to what we assumed would be the worst bath, which was at 0, 30, and we were right. And that is measuring obviously at 100% since we're doing it relative. And then we do see a significant decrease even doing those 2 minutes in the 2 gram per liter bath. And it just goes down from there. You can also note that the red on this chart represents the amount of bleeding in the 20 gram per liter bath, and the blue represents the amount of bleeding in the 2 gram per liter bath. So for all of those, and from the 228 onward, most of the bleeding is occurring in the 2 gram per liter bath. This is a good thing. This means that this bath will have to be replaced sooner, but because there's less chemistry in there, it'll be more inexpensive to replace and less waste treatment will be needed in the long run. Next, looking again at seal quality, adding those 10 minutes did greatly increase seal quality across the board, especially for that 0, 30, and 30, 0. But we still see very good results for the 426 and 624. So this is kind of telling us that combined doing that 2-step process and adding those 10 minutes, we will see a significant decrease in dye bleed and a significant increase in seal quality. All right, so just to reiterate what we just discussed, using this 2-stage process, the first stage being the 2 gram per liter mid-temperature nickel-free bath, and then the 20 gram mid-temperature nickel-free bath. We saw excellent seal quality results, running it at 30 minutes, a good reduction in dye bleed, about 65 to 75% using it, versus just doing that 20 gram per liter stage 2 alone. For our third and final test, we replaced the 2 gram per liter nickel-free bath with mid-temperature water. We did again add that 2 gram per liter additive just to ensure everything is going according to plan. It's also important to note here that because we have that additive in there, these 2 steps will have to have a rinse in between because the chemistry is different. Meanwhile, when doing test 2 and having 2 nickel-free seals, no rinsing is required because the chemistry is the same, so no cross-contamination can happen. Again, we had the time breakups going from 0:30 to 30:0, as you can see in that second chart. And this will again give us something to compare those middle results to. All right, so let's look at those results. For seal bleed, we again did it relative to that 0:30 bath, which we knew would be the worst, so that's measuring at 100%. The red is again bleeding in the 20 gram per liter nickel-free bath, while the blue is bleeding in the water. We do see an even bigger decrease in bleeding using water over the nickel-free seal, but more of that bleeding does end up happening in the 20 gram per liter nickel-free seal. And then for those seal quality results, these results are not as good as having that first step being the nickel-free. For comparison, with that 426 combination, you can see here that result is around 1.5 milligrams per inches squared, while when we did the nickel-free seal at 2 grams per liter as the first step, that result was closer to around 0.6 or 0.7 milligrams per inches squared. So a pretty significant increase. You'll also see here that that 10-20 combination is basically on the verge of failing. I would say it's borderline at best. Meanwhile, having the seal time being completely in the mid-temperature water, that results around like 7.2, which is a hard fail. This is because when you are using water as a seal, the main thing that is sealing at that point isn't the chemistry, it's the heat. So having it not be as hot is it's not doing the job as well as it needs to be, which is kind of referring back to what I said earlier for using water. You have to keep the heat up in order to get a good seal quality. So let's kind of look at those conclusions we just made. For a 30-minute 2-stage seal using mid-temperature water and then a mid-temperature nickel-free seal at 20 grams per liter, we saw good seal quality results, not as good as in test 2, but still good, but an excellent reduction in dye bleeding, about 75 to 85% versus using stage 2 alone. So for Lightfastness, we ended up doing a 200-hour fadometer. These results are measured by using the delta E, or a change in overall color from the standard. All of these results are really good. For these panels, all were sealed at 30 minutes. We again did a hot nickel, a mid-temperature nickel, a hot water, a mid-temperature nickel-free, and then one of the combinations from test 3, that 228 with the mid-temperature water, then the mid-temperature nickel-free. The best results on here are that hot nickel and the 228 split, which is showing us that it is comparable when it comes to Lightfastness results, which is really good for us. All right, so I'm going to kind of briefly go over all these seal chemistries again, just to give you kind of a bigger picture of the pros and cons when it comes to using these. First, with that DI water, it is inexpensive to make up. It's easier to dispose of because of the lack of heavy chemicals in there. The cons, however, that it is high temperatures, so that high energy costs can be astronomical. And if you don't keep that heat up, it can lead to worse bleeding, worse seal quality results, and worse Lightfastness at the end of the day. And then for that hot nickel acetate seal, again with the smut suppressant, pros is that there's low bleeding, good seal quality, good Lightfastness. It's basically a win-win-win, except for it does have a very short bath life. These seals are only meant to last a few months at a time. The high temperature does lead to very high energy costs. Smutting can occur if everything's not kept in range, and more waste treatments needed than doing the DI water option for a hot seal. Next, we have a mid-temperature seal. Again, these operate by hydrating the surface on a molecular level, similar to the hot seal, but that addition of the surfactant is used to increase seal quality. The con for that, though, is that using a surfactant will also increase dye bleeding, which is not a great thing. The pros, though, of using a nickel acetate mid-temperature seal is that there's a lower temperature, longer bath life, good seal quality results, and decent Lightfastness. Not as good as using its hot seal alternative, but still good. And it does overall have worse seal quality and dye bleeding compared to that high temperature counterpart. When it comes to nickel-free seals, We kind of saw it at the beginning. The pros are it's a lower temperature, longer bath life. It's nickel free, which we really want, easier waste treatment because of that. And it does follow regulations. Like if you're in California, it'll follow Prop 65. However, the cons for this is there is worse dye bleeding. The seal quality compared to other single step counterparts, all the other ones we're looking at, is worse overall. But if you make that into a two-step, we get similar pros from using a single-step nickel-free, but we also get better ADT, better, or we see less seal bleeding, and we get better light fastness results. Cons is it does require two steps. So if you're using water as your first step, you'll have to have 3 seals total for a rinse seal and a rinse tank somewhere in there. And then you'll have to have the room, and some people just don't have the room for that additional tank. Finally, we are going to talk very briefly about the low temperature seal, the nickel fluoride seal. We didn't do any testing on this in regards to using it for in regards to comparing it to the other seals, but I did want to briefly go over the pros and cons, just so you have a very well-rounded picture of what you're going to be getting into. Pros with using a low temperature seal: it does have a very long bath life. So while the hot seals are meant to last a few months, maybe 6 months at best, a low temperature seal can last a year or even longer. This means to lower costs when it comes to remaking up that bath. It also requires little to no heating, which is great. That means lower costs during the operating times. And we also see decent seal quality and dye bleed results. Cons: it still does have nickel. Fluoride concentration does need to be maintained. Seal quality and dye bleed results can be a little worse because that heat is not there to help it along. The other con of using a nickel fluoride seal is that because the heat is not present to move the sealing process along, you either need to give it time to cure or you need to have a hot dip directly after. Otherwise, you should not be even touching the parts after it comes out of that nickel fluoride seal. It will leave prints because it hasn't had time to cure. I do also want to reiterate that light fastness and dye bleeding have very large effects on the maintenance and activity. Oh, I'm sorry. Light fastness and dye bleeding greatly depend on the maintenance and activity of the dye bath, as well as the dye used. So these numbers are working well for this dye specifically, the dye that we use during these tests, but some other dyes will not react as well. A lot of red dyes will bleed a lot, no matter what, etc. So in conclusion, a good nickel-free alternative to seal black anodizing is a 2-step seal process of a combined 30-minute duration. That first step would either be a brief treatment in mid-temperature or 185-degree water, which would lead to less bleeding, or in a mid-temperature diluted nickel-free alternative additive for better seal quality. That second step is a longer treatment in a conventional mid-temperature nickel-free seal to ensure good seal quality, etc. So as we saw through those tests, seal quality, dye bleeding, and light fastness results are comparable to doing a 20-minute nickel sealed black anodize. The first stage, that water or the diluted nickel free, can be dumped with minimal chemical loss and remade up with minimal cost in general. While that second stage does promise to have a longer life and extended use, as mid-temperature seals can usually last 6 months to a year. All right, so thank you so much for listening to our presentation today. I really hope you learned something valuable from it. On the next slide, I am going to leave it up for a minute. It's going to have the actual chemicals that were used during these tests. If you have any questions or concerns about either this presentation or the products used in general, don't hesitate to give us a call. We would love to hear from you. Thank you again and have a great one. Bye.